Hello, everyone. Thank you all for joining me today. I'm Judy Piper. I'm one of the engineering leads at C Labs and also the host for this Celo Tech Talk series. Celo Tech Talks is one of many Celo Foundation's efforts to share and spread Celo technology knowledge with growing Celo community. We started this learning journey with you early April this year. Some of you may know it was initially intended to be an on-site event at C Lab's Berlin office, but due to COVID, the event had to be moved to online. It's hard to believe it's already October, and for the past 6 months, we've had more than 10 educational sessions on building Celo, starting at a very high-level overview of Celo to deep dive on each building blocks of Celo platform. We strove to make the content accessible and inclusive to anyone who wants to learn about Celo technologies, from mobile applications to distributed systems to blockchain to cryptography to infrastructure. In April, John and I gave the first Celo Tech Talk to introduce Celo as the mobile-first full-stack blockchain platform and how we made architecture and design decisions to support Celo's mission of building an inclusive financial system. Gradually, we introduced you to various Celo building blocks, Celo SDK for dApps developers, and how you can easily start building on Celo to Celo's proof-of-stake consensus algorithm to stability protocol to Plumo ultralight verification sync protocol to governance protocol, and most recently phone number privacy and many more. For those who missed the previous sessions, we gave the recordings available. We have the recordings available on Celo Foundation's YouTube channel, and Celo Tech Talk series actually has its own playlist in a chronological order. So as you watch them, please give you a thumb up or a like, and then leave comments if the talk was helpful to you. And I've also written a Medium blog post to summarize each Celo Tech Talk. So be sure to check it out and give them claps. How many claps you want? There's I think 50 limits, and I'll be sending out a follow-up email with the links to Celo Tech Talks playlist as well as a Medium post after this talk. So this week we have Kevin Jewett, a protocol engineering partner at C Labs, and he's going to give a deep dive on Celo blockchain and client code. Kevin, welcome to Celo Tech Talk. And as always, I like to start with the introduction to presenter. Would you like to share your how you joined the C Labs and how you got to work on the Celo?
Sure, thanks, Judy. So as Judy mentioned, I am a protocol engineer at C Labs, and I work on the blockchain team. And I have been at C Labs for about 2 years. So before joining C Labs, I have worked on large-scale and interesting distributed systems and database problems at companies like Oracle and AWS. However, I really wanted to find a missions-driven company with a very strong good mission, a very strong common good mission. But at the same time, I wanted to find a place that did work on cutting-edge technologies and had a rockstar team. And Celo basically provided, well, C Labs specifically provided all that. And that's basically how I ended up at C Labs.
Wow, thank you. Would you like to get started then?
Yeah. So for this talk, I am going to give an overview of the Celo blockchain client. I am then going to do a code deep dive in some of the main features that we implemented for it. And so just the high-level agenda of this talk is that yeah, I'll give a high-level overview of blockchain clients in general. And as part of that, I'm going to touch a bit into the Ethereum client. And then I'm going to do a deep dive of some of the main features that we've added, which So this is certainly not a comprehensive features that the C Labs have added to our client, but I think this is a good representative set. And after that deep dive, then I plan to discuss some of the future features that we plan to implement. And then I'll open, so Judy and I will then open it up for Q&A. So I want to first remind everybody about Celo's mission. And that mission is, so our vision is to build a financial system that can create conditions for prosperity for everyone. And to that end, we decided to leverage the potential of blockchain, basically its trustless nature, and smart contracts. But at the same time, we wanted to be sure to meet user needs and create a very, very useful and easy to use product. So ultimately, we decided that we had to go with the full stack approach to meet those needs. And for this talk, I'm going to focus on the blockchain layer, I guess the lowest layer right here in this graphic. So I'll first start off with a quick overview of what a blockchain is, and then discuss some of the distinctive parts of the Celo blockchain. So at its core, a blockchain is a highly replicated database with an immutable transaction history. Now, all this data must be approved by a number of miners or validators, and normally just they're normally similar. They have similar roles, but just different terminology. So miners are for proof of work blockchains, and validators usually are for proof of stake blockchains. And blockchain systems normally bake in rewards and penalties to incentivize correct behaviors of these validators. So also, most modern blockchains contain a compute engine, and this is like a lot of this is what basically powers the smart contract layer, and this compute engine provides the ability to add more generalized logic. So you can think of like Bitcoin, that for every transaction it has very limited logic capabilities. Specifically, all it does is just transfer tokens from one address to another. But with this compute engine, a developer can provide more powerful logic for these transactions. And just one hypothetical example, and this is certainly not something we've built, but it is possible to let's say embed like some tax code rules within the transaction. So whenever a transaction is executed, then based on the sender and the recipient of the transaction, part of that value transfer then can be directly applied for taxes. The thing, though, is that a lot of the original blockchains did have issues that make fulfilling Celo's mission very, very challenging. So, for example, Ethereum and Bitcoin, they both had slow transaction rates and long transaction finality times, up to an hour. And this is because of the proof of work consensus engine. And additional to that, there was really relatively high data requirements to maintain security and trustlessness. And what that means is that many of our target users who only have a cell phone, and they are in environments with very extremely cellular data restricted environments, or they have very high cellular data rates. So these cell phones, their application must download a good a relatively large amount of data from the blockchain to ensure that the blockchain that they're reading is correct. And this would be a challenge for user adoption. So because of these issues, the C-Labs team decided to create our own blockchain that would be specifically engineered to be mobile friendly. So to kickstart our blockchain, C-Labs first evaluated a number of current blockchains, and this is about 2-3 years ago. And the decision was to fork one instead of creating our own. And a lot of this is to speed up the initial development. And at the time, Ethereum was the best option. And mostly around because it was the most used programmable blockchain. And also it had the best developer tooling and ecosystem at the time. Now, within Ethereum, so there are two main clients. So there's the go-ethereum, which it's commonly referred to as Geth. And then there is, at the time, what is called, it was Parity's client. So Geth did actually have better light client support. So that was the big reason why we've decided to fork from Geth as opposed to Parity, which is now Open Ethereum's implementation. And again, just to remind all users that our blockchain was engineered to be mobile friendly. So this light client support was a very, very important factor. And forking from Geth did actually provide some other advantages as well. So any major features any major future features that has been implemented and committed into Geth, we can also basically kind of pull that commit into our Celo client code base as well. And not just for Geth, but any client that is derived from Geth, where any changes to those derivations, we can also merge those changes into our client as well. And I think one great example is this one project called TurboGeth. So it is a very highly optimized version of go-ethereum. And it has a lot of changes to how it stores and processes the state. So we are currently really considering to see if we can basically adapt to those changes into our client as well. So after forking from the go-ethereum code base, the C-Labs team decided to add the following features. And again, this is not a comprehensive list, but I think it's a few features that we have highlighted in the past. So one of the most important features that we had to add was a proof-of-stake consensus engine. And again, the end user reason for this is so that we can increase the transaction throughput of our blockchain, as well as reduce the finality time. We then added in fast sync for our ultralight clients, which are which reside in our mobile app, or the Valora mobile app. And this is actually it's a combination of features that we've done for this one. And then I will touch upon some of the more, I guess, the sub features later on in this talk. Another big feature that we did is transaction gas payable in multiple currencies instead of just the native Celo token. And the reason for this is that from our user feedback, we found that it was hard for many of our end users to kind of, I guess, have to wrap their heads around the fact that they have to have two different currencies. So most likely they'll be using our stable Celo USD currency to actually make payments, but then without this feature, they would actually have to also have Celo token to pay for those transactions, which is not a very intuitive thing. And one other aspect I'd like to mention is that when we so when we forked from Geth and Ethereum, we also made sure that our client would be EVM compatible. And the big reason here is that so we can maintain and kind of leverage a lot of that existing developer ecosystem and developer tools. All right, so so I'll first start off the deep dive portion of the talk of how we implemented our consensus engine. And I'd like to remind everybody here that Tim actually did have an earlier talk in this Tech Talk series about consensus and proof of stake. And I recommend, like, many of these attendees to go and go back and watch that. And his talk discusses a bit more of the theory of this component. And I'm going to focus more on the implementation of it. All right, so a quick reminder from his talk. So the Celo network, it does contain a number of different different node types. And kind of at the center of it is the validators. And then you have the full nodes, and then you have the light clients. And the light clients all reside within our Valora mobile app. Now, the validator's job is to determine what are all the Celo blockchain's new blocks. And to do this, they all run a consensus algorithm, and an algorithm that is similar to, for those who are kind of, I guess, knowledgeable about distributed systems, is an algorithm that's similar to Paxos or Raft, which the Zookeeper and the etcd systems use. Or actually, well, yeah, I mean, there's that's not exactly true, but in general. So the validators, at least, so a big difference between Paxos or Raft is that for our consensus engine, at least 2/3 of the total number of validators must be non-faulty for consensus to be reached. And what non-faulty means here is that they must be honest and they must not be down. So for our consensus engine, we decided to use the IBFT consensus engine early on, the Istanbul Byzantine fault tolerant consensus engine. So this engine is actually quite well used in the blockchain community. So the Quorum and Pantheon clients, Quorum, I believe that they work with JP Morgan, that they also use this consensus engine, and I believe that it is actually being used in over like hundreds of deployments right now. And this consensus engine actually fit our needs for a proof-of-base system, at least for the short to immediate term. It provides us that fast finality of transactions and good enough transaction throughput for the early years of the Celo blockchain. The thing is, though, that like the first versions of IBFT did have a few faults. And a lot of these is actually described within this the Pantheon's paper, which is linked here in the slide. But and so the initial version of IBFT, it used a locking mechanism to ensure safety during round changes. So for example, like let's say, so during a specific consensus round, let's say the proposer was down. So it had to use this locking mechanism to ensure that that all the validators will correctly go to the next proposer, and then they will continue on creating blocks. But the thing is that this locking mechanism actually did have a liveness issue. That again is described within this paper here, the Pantheon's paper. So what we did is we replaced that locking mechanism with a what is it, like a PBFT style round chain certificates. And I think again I refer to Tim's talk too, so he'll go more in depth into exactly what that is. So we've also the initial version of IBFT used gossip to communicate consensus messages among validators. And from our load test, we found that this gossiping of messages actually did affect the consensus time, and which ultimately affects block time. So we made changes for that, and I'll kind of go in depth in that later on this talk. And there are a whole bunch of other like security and performance improvements that we've made to the engine, which I'm not going into detail, but just kind of wanted to bring it up here because those were actually very important improvements that we did make. All right, so here, so this slide, so I know the slide is a very, I guess, very dense one. So not asking you to kind of read too much into it, but I think the main takeaway here is that so as part of the consensus algorithm, every validator is going to go through a set of state transitions, and this graph like details that. But again, don't go too much into detail here. So for example, like all validators will start in this accept request state, and then based on certain events that they would transition to different states. And then they will all like eventually go into this committed state, and that is when the block is actually finalized. Now, for the actual code implementation, so that the consensus code is all implemented in this core package as highlighted in the slide here. So within this package, there is a Go file for every one of the message types. And within each one of these Go files, it will contain logic to constructing each one of these messages. And I think more importantly, it also contains the handling logic of when it receives that specific type of message. And this handling logic, like in general, what it does is that it would verify the message, and then if certain events or criteria have been met, and kind of going back to the state transition diagram, if certain criteria has been met, then it would transition the validator to a new state. So for example, for the pre-prepare message, so this message is meant for when the proposer of the consensus round wants to send out a block proposal to all other validators. So it would use this pre-prepare message to send it out. All the validators would receive it. They will verify that this block proposal is actually correct. For example, all the transactions that's included are valid. And once a validator has received that pre-prepare message, then it would then send out a prepare message. It will send out a prepare message, and then transition itself to the pre-prepared state. And again, these files basically contain logic for all of that. So in addition to containing the logic for this the state transition diagram that I showed before, it also contains a round state database. So this database is a LevelDB instance. And for those folks that don't know what LevelDB is basically a kind of like an embedded key value store. And like, just like, really roughly, like you can think of it as like a file, but then it has a key value interface for that file. So this package does contain a LevelDB instance where it will persist that data, or persist a lot of the consensus data. For example, it would persist like the validator's current consensus, the current round's block proposal, and like save all of the received messages from other validators as well of the current round. And the main reason we've done this, we added this is so that to handle the case when the validator does go down during consensus. And for those cases, like if the validator does not remember its own state, it could actually end up sending different messages of the same type within the same round. And it could lead to the validator double signing a block, which is a slashable offense. So it was quite important to make sure that the validator would essentially persist and in effect remember a lot of its state in case it ever, the consensus state in case it ever does go down during the consensus round. So so now I'm going to transition a bit to another feature that we implemented. So so as I mentioned earlier before, the initial version implementation of IBFT, it used gossip to communicate messages among validators. And we did see that it does impact consensus time. And you know, the consensus time is something that we want to minimize as much as possible so that it could result in faster blocks and, you know, result in faster finality. And you know, actually, we are still in the process of doing much more work of trying to, you know, decrease this consensus time. But this was one of the first, first optimizations that we saw that we had to make. So to address this kind of low latency gossip mechanism, we've created the announce protocol. And what this protocol does is it allows all the validators to privately communicate their IP address to each other. And then once the validators know of, like, you know, all the other validators' IP address, then they can create a direct TCP connection to each other. So in effect, kind of create like a mesh network on top of our P2P network. And these validators will then use these direct TCP connections to send consensus messages to each other. And again, so this is all to reduce the consensus time. So the actual implementation of this protocol is done within this Istanbul backend package, as highlighted in this slide. So so within this package, it has a file announce.go, and this file contains the message definition and all the message handling logic. So it's very similar to what I kind of mentioned before about the core package, about how it had separate files for every message type. Before in this case, all the messages are within announce.go. So similar to the core package, the announce code also has a level of DB instance. And what this DB instance is used is to persist the remote validator's IP addresses. And again, you know, this is done so in case of the validator goes down, then it does not have to, you know, rerun the announce protocol to discover all the other validator's IP addresses. And one thing I did want to highlight about our announce implementation is that it also implements a separate Go routine event loop. And basically, so what this event loop, you know, what it does is that it's running in a separate thread, and you know, you can think of it as running kind of in the background, and it would manage any events that has arisen that is related to the announce protocol. For example, like one event that is relevant to the announced protocol is when a new validator has been added to the validator set during a the epoch election, epoch validator election. So when that happens, then then all the validators will then have to figure out what is this new validator's IP address, and then basically this go routine is going to drive that process. So the reason why I wanted to bring this up is that this is actually a very common design pattern in much of our code that we implemented, as well as much of the original Geth code, being that like having a separate go routine event loop that would manage events for a specific component. All right, so I'd like to also now discuss a bit about our proxy implementation. So again, like Tim, in his talk, that he did really just kind of go in depth about the proxies and their purpose, but I'll give a quick overview of what they do. So as a result of these direct TCP connections that our announced protocol that it provides. So one potential security issue with these direct TCP connections is that all validators will know of all the other validators' IP addresses. So if any one of these validators is malicious, then they could just launch a DDoS attack on other validators, and then that will ultimately halt the Celo blockchain. Because like as I mentioned, we need at least 2/3 of the validators to be up and healthy for consensus to be reached. So to address this potential security issue, we've created the proxy node, and their main purpose is to protect the validators. So these proxies will allow validators to be run within a private network. And because they are running a private network, it would also provide more protection in attackers and trying to break into the machine and try to retrieve its private key. And the proxy is basically the validator within the private network will be connected to the proxy, and the proxy basically provides external network access for this internal validator. And because a validator can connect to multiple proxies, if one of the proxies goes down from just regular machines getting restarted, or if it's actually being attacked, then the validator can then use its other proxies to make up for the proxy that actually did go down. And one other important note that I want to kind of mention is that the proxies, they would receive all the messages from the external network, and then they will do all the authentication and verification of those messages before it forwards it off to the validator. So that's part of its protection it provides for these validators. So the implementation of our proxy is located within this Istanbul proxy package. And this package contains two main objects. So it's one of these objects is the proxy engine object, and this object it's used by all proxy nodes. And as I mentioned, this object will verify all announced and consensus messages that it receives from the external network, and forward the ones that are verified to the proxy validator. And this object also handles messages that the proxy validator will send to the proxy. And for example, one message that the proxy validator sends to the proxy is what we call the val enode share message. So as I mentioned, a validator can have multiple proxies, but the validator will then have to tell each one of the proxies which remote validators they should connect to. And basically the proxy validator will communicate that information via the val enode share message. And the handling of that message is all done within the proxy engine object. And the other main object that this package implements is what we call the proxy validator engine. And this object is created by all validators that are being protected by proxies. And this, so the main logic of this object, it's all implemented within a go routine event loop. And similar to the announce go routine event loop, that it would also basically listen to any events that are related to its proxy handling. So for example, let's say a new proxy is added, which a user can do via the RPC API, or if a proxy has been detected to be down, then this go routine will then handle it. So it would be notified of that event, and then the go routine will then basically redistribute like which remote validators each proxy should connect to. And then it will then communicate this new kind of assignment of remote validators to proxy via a val enode share message that's being sent to each one of the proxies. All right, so yeah, so those components that I just kind of mentioned, I guess the IBFT consensus engine, the announce, and then the proxy. So they all basically like encompass, basically consensus and providing security, and then providing the fast finality features of our client. So now I'm going to kind of transition a bit more to I think other high-level features of our blockchain client. So more specifically, I'm going to discuss the fast syncing for our ultralight clients. So as I mentioned earlier in this talk, it is very important that our Valora, the mobile payments app, uses very like low amount of data for its light clients. And again, because like a lot of our end users, that they will be in very cellular data restricted environments. So to that end, we've actually made a number of changes for that. So one of them is BLS signature aggregation. So what this does is that it actually, so the end result is that it actually drastically reduces the size of our block header, which the Valora app will have to download. And I'll get more into detail about this later, but at a high level, what it does is that it aggregates a whole bunch of different validator signatures into one. So one other change that we made is what we call epoch-based syncing. So in the original go-ethereum, all the light clients actually had to download every header for every block. Now, certainly downloading a header is much more, it has much more less data requirements than having to download the whole block, but still, like having to download like thousands, or millions of headers it's going to be expensive data usage wise, and especially for our blockchain that we have block times of 5 seconds. So the number of blocks that the block rate for our blockchain is going to be much higher than Ethereum right now. So to address that issue, we did the epoch-based syncing, and what that means is that the light client will only have to download one block header for every epoch, which happens, once a day. So that resulted in the light client only having to download one block header to what originally was close to 20,000 block headers. And the thing is that it also does not impact like security and trustlessness at all. So within each one of our epoch block headers, we've actually embedded we embedded basically what we call the validator set diff. So with these epoch block headers, the Valor app will be able to essentially calculate what is the current validator set for the current head block. And one other very exciting feature that we are currently working on is our Plumo-based ZK snarks-based syncing. So these snarks will allow light clients to certify validity of 1 year's worth of epoch block headers. So that drives the data usage requirements even further. So instead of having to download one block header per day, when the Valor app is syncing the blockchain, instead it would just need to download one snark per year. All right, so I'm gonna delve a bit into the implementation details of the BLS aggregated signatures. So BLS aggregate these signatures, yeah, as I kind of mentioned that they allow for aggregation of signatures, and what that means is that it will allow many signatures that are signed by different private keys to be combined into just one. And during the verification of this BLS signature, the verifier will know which key did actually sign, or the verifier will know the keys of all the individual signatures that have been aggregated into this one signature. So in the original IBFT implementation, all the headers actually had an array of signatures, for all the validator signatures. So just a quick reminder, when a validator has committed to a block, then they will then add their signature onto the block header. But the thing is, we need two-thirds of the validators to be able to sign on these blocks to ensure that this block is actually fully finalized. And because right now we have a validator set of 100 validators, that means that we'll need 67 signatures on the block header. And these signatures are each one of these signatures is 64 bytes long, and because we have 67 of this is not a trivial amount. So in terms of the actual code, so this code was forked from the Xexi Rust library, and then the link to that is here in the slides. And the Xexi library is quickly becoming one of the standard libraries for cutting edge crypto. And as kind of like, I guess, our common playbook, like we basically decided to fork this open sourced and kind of reputable package, and leveraged a lot of that for our BLS signing. And we also had to do a lot of integration code between our this BLS signing code and then the IBFT consensus code. And all that integration work is done basically within the core package that I described a bit earlier in the talk. And then another important thing is that we had to add new header fields for this. So within this istanbul.go file, it has the definitions of much of the block headers fields that we've added. And here you can see that we had to add basically two fields. So one is the signature field, which basically does contain the BLS aggregated signature, and a bitmap field, which stores the information of which of the 100 validators, which of their individual signature is included in the aggregated signature. All right, and let's see. So I'd like again to transfer to one other kind of high-level feature that we implemented, and or transition to, that is. And this is the Celo dollar transaction fees. Yeah. So again, as a reminder, we decided to add this feature based on user research that we've done, and from that user research, we found there's a lot of user experience friction when users wanted to pay, wanted to transfer CUSD, and specifically that they had to require that it required that they had the Celo token to actually do the transfer. So to address this, product and user experience friction, we've added the ability to pay transactions, but with CUSD. And to do that, we've added a field in the transaction to specify which currency to pay the transaction fee. And so right now, like CUSD is supported for currency payment, but new currencies can be added in the future through our governance process. And so we did also actually have a talk earlier in this Tech Talk series about governance. So certainly, recommend folks to for that talk who want to kind of get a better understanding of it. All right, so the actual implementation of this feature. So we had to modify a number of components within our client to support this. So the components that we had to modify is the transaction pool, the state transaction object, and what originally has been called the miner object, just because of the kind of proof of work legacy of Geth. So those are the three objects that we had to modify. So for the transaction pool, we had to add support where whenever a transaction, whenever a node discovers a new transaction, but one that has not yet been finalized on the chain yet, it would have to verify that transaction balance. And if that transaction is using Celo dollar to pay for the transaction, then it would actually have to make sure that the sender of the transaction does have enough Celo dollar. And once that verification is done, then the node will then add this transaction to the transaction pool. Another place that we had to modify is the state transition object, and much of this this object this responsibility is to basically handle, like, when a transaction is executed, it must handle how the state should the resulting state of the transaction be, right? So specifically, if let's say the user is paying with US dollar, USD, CUSD, then this state transition object must make sure that the corresponding, like the recipient and then the sender's like ERC20 CUSD balance is correctly debited and credited, and all of that done is implemented within the state transition.go file. Now for the miner object, so normally what this object does is that it creates block proposals, and we have to modify it so that it would create proposals such where the transactions within it would have the highest normalized fees. So what that means is that, so you can imagine that many of the transactions within the transaction pool will have many different currency types. But then the miner or the validator in our case, like they want to choose a block where they can maximize the number of like the transaction fees, because they'll get like a portion of it. So that means that we had to modify the worker.go so that when it chooses transactions from the transaction pool, it actually had to do a kind of a so for all transactions that's not being paid in the native Celo token, it would actually do a quick exchange rate from, let's say, CUSD to Celo. And basically normalize the fee to Celo so that it can determine what is the most, the highest, like, it'll determine the transaction of the highest transaction fees. And to do this exchange rate, it actually uses objects within the Celo blockchain contract com folder. Now, I wanted to kind of so this slide, I believe it's has been shown in other tech talks, but basically our system has a whole bunch of, and this is more into our higher smart contract layer, but it contains a whole bunch of what we call system smart contracts. And these smart contracts our client, our blockchain client, will be able to interact with them, and actually from the internals of it, it can actually execute transactions. So that interface between the low-level blockchain client code and this like layer 2 system smart contract code, all that interface is done within this objects within this contract com folder. And kind of going back to this CUSD transaction fee feature, what it does is that it would use one of these contract com objects to basically retrieve the exchange rate between Celo US dollar and Celo. And to kind of cover off on this feature, I wanted to mention that we did have to create a new field for the transaction, and we had to add this fee currency field, which is basically the address of the ERC20 token, into the transaction object, which is defined within transaction.go. All right, so I did go through like a number of the features that we've added, and it's certainly, like I want to mention again, it's certainly not comprehensive, but here I wanted to kind of describe some of the future features that we plan to implement. So for example, like we want to increase transaction scalability, because as we get more adoption, that we're going to have to be able to increase the transactions per second that our blockchain can handle. We want to increase our validator set size so that it will increase security of the blockchain. There's a few features that are currently in progress. So as I mentioned, the Plumo sync, that's currently in progress as we speak. There's full node incentives, and also latency-based full node discovery. So where our Valora mobile apps that they can find full nodes that are geographically close to them, or at least where has the minimize the latency between the wallet and the node. And again, this is just a very small snapshot of many things that we plan to do. But I also want to stress that all of these features they're all ultimately for our mission of providing conditions for prosperity for all. I mean, they're all certainly all very interesting tech problems in its own right, but we want to make sure that what we implement is does meet our ultimate mission.
Kevin, we are a few minutes behind. Can we move to the last slides?
Okay.
Thank you. Before we go into the Q&A, we may have 5 minutes for the Q&A. I'd like to make a quick announcement. Next week, we invited Mike Feng, CEO of Hummingbot, to talk about Hummingbot and how the Celo community can utilize the liquidity mining tool on Celo. And Michael will also give us a demo of how to set up Hummingbot. So please join us next week. And now on Q&A, we have 2 questions. Hi, Kevin. My understanding is that nodes have been running out of memory, and in some cases, the databases gets corrupted. Is this an issue that came over with Geth? Are you aware of it? And if so, is there a fixed plan? Gavin from Figment.
Yes, so we are certainly aware of it, and we did make some changes to fix that, and those changes should be going out within our 1.1 release. So to be honest, I'm not the I'm not managing, I guess, our release process, and I think hopefully you can get in touch with Mariano and Pranay who are doing that. But from what I understand, our 1.1 release is already been deployed on some of our testnets, like Bakuva and Alpha Horus, and should then be shortly be basically given the green light to be pushed off to mainnet. But yes, we are certainly aware of that and already have pushed some fixes for that.
And would you be able to follow up with Gavin on Discord?
Yeah, so Gavin, I can certainly do that over Discord.
Thank you. And the next question is a repeat question from Umar. Take 2 clients using 2 different languages like JavaScript and Go to render the same blockchain, for example, Celo or Ethereum in real time. Are they working on the same blockchain in different program languages, or is a different client implementation essentially a different blockchain altogether?
Yeah, so Celo specifically, right now we only have one implementation, and this is the one I just kind of described to you. But for example, like in Ethereum, there is many different implementations and done in different different languages. So so Ethereum, they have the Rust implementation and their Go implementation, and they're both widely used. So and they both work interchangeably very well with each other. And so, but then fundamentally they what they all have to agree upon is basically just like the protocol rules. And in the future, certainly, we do kind of envision that other entities will implement implement our protocol in different languages, and I think that'll just make the Celo blockchain itself more healthier, because you have different implementations, so you don't quite have correlated failures in case there's a bug in one. So, and also just kind of broaden the whole developer community. So that's something that we're looking forward to happening for Celo.
All right. Thank you, Kevin, and thank you everyone for joining. And see you next time.
Thanks, Judy.
Yeah. Thank you. Bye.